Anchors away. Hello, everybody. Mr. Record here from Avon High School. I'm going to talk to you about topic 8.14. Yeah, anchors away. We're going to go on a little sailing voyage here. Topic 8.14 is not a topic in the calculus course and exam description from College Board, and so work is not a topic that will be tested on the BC exam, but as with all of my other videos that I had mentioned before, this is a very popular topic that would be often encountered in a college Calculus 2 course. And it's usually this kind of problem that starts to get students just a little bit of difficulty because of this extra little component. Let's take a look at our problem. So as we can see from above, it says that we got a ship that's anchored in 100 feet of water. The anchor is going to weigh 4,500 pounds, and the chain that it's attached to weighs 25 pounds per feet. So you got to keep it in consideration that we can't just use any simple rope to lift up this anchor because of the weight. And so we have a pretty robust item in this chain that's also likely made out of iron as well. Now, before the ship sails, the anchor has to be pulled into the ship, and we want to know how much work is going to be needed to bring the anchor and the chain into the ship. Now, a lot of the information here that I have basically talks to you about the different options that one would have to label and set up the problem. And I've got two different options here, as you can see. One option will have students use the x-axis as the bottom of the seabed. So this little dark black line could be our x-axis. Now, if we choose to do that for our x-axis, I'm going to use a different color, our y-axis could look, oh, maybe something like this, just something drawn vertically. I just don't want to cover up all my information there. And so that could be the y-axis. Now, what that means is that the position at the very bottom of the water level where the anchor would initially be could be the point 0, and then the point at which the anchor could be raised up to the ocean level, sea level, would be the point 100, because after all, it was 100 feet deep. Now, the other option, not so sure I'm a fan of this, but you could have put the x-axis up here at sea level. Now that causes for a very interesting setup for your other ordered pairs. 0, is now sea level. 0, -100 would be where the base of the bottom of the sea would be. And I don't know if that's quite as intuitive to me. So I'm going to choose to do this problem by putting our x-axis at the bottom. Let's take a look at our solution now. So here we are back with our problem, looking at part A. If that anchor is at the bottom, and if we were neglecting buoyancy, how much work would be required to bring just the anchor, not the chain, aboard the ship, or at least in this case, to sea level? And so when we do a problem such as that, we are only going to be dealing with a very static kind of work. In other words, we said that the anchor does weigh 4,500 pounds, so therefore it would take 4,500 pounds of force to get it to move. And if we're going to bring that anchor a total distance of 100 feet, then those two things multiplied together would be what, 450,000. And once again, our units would be pounds over here, feet over here, so that's our typical foot-pounds, our imperial unit, right? A little bit different than what you might see in a physics class with Newton meters, but the idea is the same. Now, it's very important that I point out that this problem is absolutely bogus. Bogus, 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 because we have chosen to neglect buoyancy. The buoyancy is going to really help us a lot in this problem. And I'm not saying that we don't have the mathematical ability to compute that. The buoyancy is going to be a little different at each level in the ocean. And so it does allow a little bit more complication to set up the problem. But it is something that we as a mankind have the ability to solve. I want to focus a little bit on the simple idea of just a static amount of work. Now in part B, it says if the anchor is 75 feet from the bottom, how much work is required to bring the anchor aboard? Well, the key with part B, and I want you to think about this for a second, we still have the same anchor that we're raising that weighs 4,500 pounds, but I want you to take a second Tell me how far this anchor now has to travel. And if you were thinking 25, you are 100% correct. All right, we're testing you out here. 75 feet from the bottom really has very little to do. Well, it has indirectly a lot to do, I suppose, with how far it has to go. But we don't want to put 75 into that spot mistakenly. So only 25 feet is what we're looking at here for our distance. And I think if we use a calculator on this, I'll spare you the details, but you get 112,500 foot-pounds. And interestingly enough, this value here is indeed exactly 1/4 of this value. I'll let you double check that. Well, it makes sense because we're only having to take it 1/4 of the total amount, 100. And because it's a very static, non-dynamic amount of work, it should have that relationship. But man, oh man, when the chain enters the picture, everything changes. And a lot of times students who are new to problems like this struggle with the idea of the chain. The idea is that this chain, if I draw many, many links of it, I know this is going to be obnoxious, right? But this is our chain. And at some point, the chain is going to have an anchor attached to it, right? Well, when we're pulling up that anchor and that entire amount of chain, that is a lot of work. That's a lot of effort on our part when that anchor is way down here. But eventually, that anchor is going to be pulled up so that it's a lot closer to the sea. And therefore, that chain itself is not going to weigh very much, right? Because most of the chain is like coiled up, inside the ship, inside the hoisting mechanism, and we're not needing to basically bear its weight anymore. All right. So in part C, it says in between the bottom of the ocean and the water, the force obviously varies linearly with the length of the chain. Now, it says in this problem, we could use both scenarios in the picture. What both scenarios are where you decide to put the x-axis. I'm going to go ahead and commit one last time to putting that x-axis here along the bottom. And so therefore, that's a thick x-axis, isn't it? And therefore, I'm going to be looking a lot more at this approach here. In other words, the values that are labeled on the left side. Had we used the x-axis at the water level, then you would have been focusing on this setup. Okay, so there we go. Let me move my x-axis a little out of the way so I can see some things. And let's move on to our part C. And in part 1 of part C, if we want to figure out the total force required to bring both the anchor and the chain aboard, well, we got to figure out first, what is our force equation going to be, our force expression. And so I'm going to go ahead and commit myself to using the independent variable y, because the force is definitely going to depend on the vertical distance that the anchor is from the boat. So what is then going to happen, move myself, there I am, is that I know that I've got to use 4,500 pounds of force. That's the only thing that's going to get that anchor moving in a non-buoyant body of water. But now I'm going to have to add some stuff. I've got to add because of that doggone chain. That chain is going to have a 25 pound per foot type of density. And so you think about this and you think, well, okay, well, how much of that chain, how many feet am I going to have to lift? Well, it depends where it is, right? When the anchor's way down here, I got to go 100. When the anchor's way up here, I don't have very much to go at all. Well, what about if the anchor is like right here at some random distance from the bottom of the sea level, which is a distance y? Now, I want you to keep this in mind. Any arbitrary distance from the x-axis in a coordinate plane is always going to have the distance y. We've talked about that a lot with some of the previous applications that have been going on here in Unit 8 of our calculus course. So that forces the distance from the sea level to the anchor to be this quantity 100 minus y. And if you think about it, that's how far we have to lift that chain. right? And it is a variable, right? It has a y in it. And so that's what we want right here. Whoops, we want 25 quantity 100 minus y. And that's going to be our force equation. And if you plug in any value of y, even if you want to plug in 100, you'll find out that this becomes 0, which basically means you've got that chain already brought in, so only the 4,500 is really that's needed to get that anchor, that last inch or so, into position. All right, so if the anchor is halfway to the ocean level, that simply means that the anchor is 50 feet off the floor of the ocean. And so we would have 4,500 plus 25 multiplied by 100 minus 50, which of course is 50. And so 4,500 plus 25 times 50 turns out to be 5,750. I'm obviously bypassing a lot of the calculator work because I know that that's going to be real simple, but please use your calculator, double check, and make sure things are coming along. Now in part 2, figure out that same amount of force when the anchor is 25 feet from the ocean. Well, here's our ocean floor, 25 feet from the ocean level, puts it up here. But the problem is our y value is what is embedded into, oops, right by my ear, right, I'm putting to it right there, 100 minus y. Our y is going to be not 25, but 75, right? So what that basically means, common sense is going to suggest that we're going to plug 75 in for the y. That way we've got our 4,500 plus 25 times what will be a 25 now, right? Because we're only 25 feet from the ship itself. So 4,500 plus 25 times 25 is 5,125. So note, it doesn't take nearly as much force to push that anchor into our ship when it's that much closer. Now, everything comes into play when we do part D. Part D is really what the question is asking us to find. Now, again, we're not going to use both scenarios. We're only going to use our x-axis at the bottom, which is going to rely heavily on this F force expression. So our work for both the anchor and the chain is going to be the integration of this force equation, 4,500 plus 25 times the quantity 100 minus y. There is our force. Now that has to be multiplied by a distance. Now this is where kids get really confused with this. If we run back to our picture, think about what's happening here. Let me clean this up a little bit. It's getting a little messy. We are going to say that at some little moment, we are going to calculate a very small amount of work that will tell us how much work it was required to move the anchor just that little teeny delta y distance. We have a force formula that's going to work at all distances. Okay, obviously it's going to vary depending on y is, but it's going to be reliable. Now, if we take that force formula, all we need to do is multiply it by that little tiny incremental distance, which was a delta y, which of course becomes a dy in our integral setup. And once we do that, all that we have to do is decide how far is that anchor going to be brought? Well, from the very bottom of the sea level to the ship itself, which is 0 to 100. You want to resist the temptation to put another instance of distance in right there. I see kids do that a lot with these problems. And sometimes I just say, hey, that distance has already been accounted for in the development of our force, right? This is a situation where we have incremental force times distance. Later on, I'll show you a force times an incremental distance approach, which is done a little bit differently. All right, hopefully you guys are okay to enter that into a calculator. and find the result. It's not a difficult thing to do by hand as well. Just maybe distribute the 25, combine some like terms. Probably going to be dealing with some pretty large numbers, so maybe using a calculator wouldn't be the worst idea. But the answer turns out to be 575,000. I'd like you to just enter that to double check. We are talking about foot-pounds here. Remember, force is always measured in 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 pounds, like in part C, but in work problems, we had, in this case, we would have a total unit of foot-pounds. All right, I hope this helps a little bit. Tackle some of those other problems that you might come across. I've got a few in my materials where you're dealing with ropes or chains that have a varying amount of force required as you start to hoist them up. So good luck in your practice, and we'll see you next time.